This is the first part of the chapter 19 on aldehydes and ketones. Firstly, I want to talk about aldehyde nomenclature. So this is the first. Well, it's not the first. It's the first carbonyl type compound, and aldehydes have to be at the end of the chain, and so because it has to be at the end of the chain, it by default will always be the carbonyl will be carbon number 1. So that means we're going to change the end of the word from an E to an AL for the parent alkane. And you need to be careful that your handwriting is clearly AL and not OL, because you may recall we did alcohols as ending in OL. And because the aldehyde has to be at the end of the chain, it's going to take priority over all the other functional groups that we've seen so far, including alcohols, and also over ketones, which we'll see in a minute. The only thing that aldehydes don't take priority over is carboxylic acids and their derivatives, and that has to do with the redox level. The carbonyl carbon for aldehydes we talked about earlier is a slightly different oxidation level than for the carboxylic acids and their derivatives, and so the order of priority follows redox level. So the higher the redox level, the higher the priority. So aldehydes are the highest priority that we've seen so far. And every once in a while you'll see the word formyl used as a group name for aldehydes, but you won't see that very often. That's kind of a common group name. And the common names are all going to contain the word aldehyde, so you'll be able to recognize them. And these common names come from the corresponding carboxylic acids, and so you'll actually appreciate some of those common names more when we get to the study of the carboxylic acids. So here's a sheet of common names. Acetaldehyde is the common name for ethanol. So that word, you could tell that came from the word acetic acid. So that's an example of one that you would probably recognize. And this ION part of the propionaldehyde, that's also a common name derived for the 3-carbon carboxylic acid. And of course we just put an AL on the end of propane for the aldehyde in there. And so here's an example with your numbering system, starting with this guy at carbon number 1. I'm not really sure why the book switches back and forth between drawing this out and showing the abbreviation, but one thing I wanted to point out is when you have an aldehyde in a line of type, it's always written CHO, and I probably have said that before, but just to sort of reinforce that, it makes it more obvious that it's not an alcohol when you see it written that way. And here's the use of the common name, the one example of an IUPAC name where the word aldehyde is actually included is when the aldehyde could not be part of the longest chain, and so they use the word carbaldehyde for that. And so when we learned in the aromatics chapter about benzaldehyde, that was actually a common name because the IUPAC name for it would be benzene carbaldehyde, kind of following this pattern. And here's your two styles of putting the number for where the alkene is inside the word versus in front of the whole root parent here. Either one of those is fine. And these aldehydes all smell good, and I haven't drawn them out here, but cinnamon and vanilla are both examples of aldehydes that smell good, and almonds, those are all aldehydes. Here's the benzaldehyde, and this is the one that smells like almonds. Benzaldehyde smells like almonds, and here's its IUPAC name. So you should learn these things, these common names, because these are the ones that you're most likely to run into. For ketones, we're going to again drop the last E and put in the word ONE at the end. And we're going to try to give the carbonyl as small a number as we can. And it will take priority over everything except for aldehydes. And if you had a molecule that contained both a ketone and an aldehyde, then you'd need a group name for the ketone, and the group name would be OXO, and you need to be careful not to get that mixed up with OXY, which was what you use for ether groups, like methoxy, which was in chapter 18. So be careful about that. The common names usually contain the word ketone, and there's an older style of nomenclature for ketones that names the alkyl groups on either side of the carbonyl. And I have some examples of that, and you will run into those out there in sort of common language used by engineers and plumbers, and I'll show you an example of that. So here's an example where we started numbering from the end closest to the carbonyl to get as small a number as we can for that. You can put the 3 for the location of the ketone either out in front or inside the word. Again, the ketone takes priority over the double bond, and so there's an example of that. Here's 2 of them. You can use the prefix di for the presence of 2 ketones in the same molecule. Common name acetone is also called dimethylketone, or DMK for short. So that's that older style I was talking about. Another common name that is one that you should probably be familiar with, 2-butanone, is also known as methylethyl-ketone. I'm kind of curious, I don't really know why they're not in alphabetical order, because a lot of the old common names, they would do that. But this one we called MEK for short. This is the solvent that's present in the little can of solvent that you use when you're gluing PVC pipe together. That's got a kind of a sweet smell, and so that's why I said plumbers, that's what they call it, is MEK. And here's an example of a ring that's a ketone. So because this takes priority over alkenes, then that in a ring situation is going to automatically be carbon number 1. And you notice that it's not included in the nomenclature that is carbon number 1, because we know that it has to be in this situation. So you just need to tell where the other things are with the number locators. And it's okay not to put the 1 for the ketone, because we know that already. Acetophenone is a common name that we learned in the aromatics chapter, and benzophenone. Again, these are common names, and these are examples of common names that do not contain the word ketone, which I said most of the common names do, but not all of them. Something else that's important that comes from sort of old style nomenclature was that ketones and aldehydes, a lot of times before they started using numbers, they would use Greek letter notations to tell where things were in a molecule in relationship to the carbonyl. So they would start numbering at the carbon next to the carbonyl and then go further away. And so the Greek letters go in order: alpha, beta, gamma, delta, and so forth. Probably as far as you need to learn for this purpose is up to gamma. And we use it to talk about places in the molecule relative to the carbonyl carbon. We've talked about nomenclature tips before. This is kind of one of those things. So in a symmetrical ketone like this, I have 2 identical alpha positions, so I've just labeled them as alpha, and then 2 identical beta positions, so I can't tell the difference. But in this molecule, it's not symmetrical, so I can call one side alpha and the other alpha prime. And I choose this side to be alpha because I've got a beta carbon here, and that's so I'm going to choose the longer side to use the plain Greek letters, and if I need to talk about the other side, then I'll use the primes on the other side. And these 2 positions are different, but they are both alpha to the carbonyl. In the case of an aldehyde, because it's on the end of the chain, you only have 1 alpha position, and then you can go on from there. And this hydrogen right here is not like the hydrogens that are directly attached to an alpha carbon, so don't get that mixed up. When you have aldehydes or carboxylic acids and their derivatives, there's only alpha, beta, gamma stuff on one side. So let's review preparations briefly. We learned about oxidizing alkenes way back in chapter 8. And what was important in that chapter was that we were cleaving the double bonds apart in this oxidation, and anytime you had a vinyl hydrogen, that is a hydrogen directly attached to one of the alkene carbons, you needed to pay attention to that, because depending on whether you used ozonolysis or permanganate, you would get slightly different outcomes. In either case, you would get a ketone if you have no vinyl hydrogens on that carbon. But in the case of vinyl hydrogens, for ozonolysis, you can stop at an aldehyde. But in the case of permanganate, it would further oxidize to a carboxylic acid. And so you needed to pick which set of reagents based on which kind of outcome you wanted. And of course, if you had a CH2 group on the end of the chain with permanganate, it would go all the way to CO2 because of the solution of carbonic acid, and is just a solution of CO2 and water. And so the carbonic acid, which is the first thing that forms, is going to degas and produce CO2. In the case of a CH2 at the end of the chain where you do ozonolysis, you just have hydrogens on both sides of this carbon, and that would be formaldehyde, and you could stop there. We also talked about the hydration of terminal alkynes. This is not a redox situation where only hydration of, you only have hydration, and you can only tell the difference in the outcomes if you had a terminal alkyne, so that you have a primary and a secondary carbon here, and you did hydration using the kind of combination of sulfuric acid, water, and with the mercury catalysis. You go through a vinyl alcohol, or enol is the more newer terminology. Well, this enol is in equilibrium with a ketone, and so the hydrogen moves over here and the electrons move here, and we'll talk more about that in a later chapter, like 22. So you can make methyl ketones, or from terminal alkynes with hydroboration, which is anti-Markovnikov conditions, you could go through the different vinyl alcohol and make an aldehyde. Now, if you have an internal alkyne, that is, where there's another chunk of carbon, it doesn't matter which set of conditions you use, you're going to make ketones. And if it's a symmetrical alkyne, you can make one product ketone, and if it's an unsymmetrical alkyne, you'll make two ketone products, and it doesn't matter which set of conditions you have those mixtures. And as I said at the beginning, this is not a redox reaction. You're not really changing the redox level of the carbon here when you go to the ketone products, or the aldehydes. Something else that we had a little more recently in chapter 17, we talked about the oxidation of primary alcohols. If you wanted to stop at an aldehyde, there was certain conditions that would let you do that. In the older books, we use PCC, or in the new book, starting with the 8th edition, the Des-Martin periodinane would let you stop at the aldehyde. Remember, from the alkenes oxidation, aldehydes are easy to oxidize, and so we had to have special conditions to stop at an aldehyde and not have it keep going. If you use something like chromium oxide in acid, then it would keep oxidizing this molecule to a carboxylic acid. And so you can use the PCC or the Des-Martins or the chromic acid, which is what happens when you dissolve the chromium trioxide in aqueous acid. You make chromic acid. All of those things are fine for oxidizing secondary alcohols to ketones, but you're just limited if you want to get to stay at an aldehyde. And we talked about that in the context of chapter 17. Now let's just go back and review for a minute the redox level that we're talking about. I did this in the preview section, chapter 18 and 3/4, and I'll do it again here just to keep it fresh in your mind. Methane carbon is the most reduced form of carbon. Officially, its redox state is -4. CO2 is the most oxidized form of carbon. That carbon is officially +4. That fits with carbon's position in the periodic table to gain or lose 4 electrons to get to an inert gas configuration. So if we look at the progression where we introduce oxygen, we go to alcohols. Aldehydes and ketones are right in the middle, and then carboxylic acids are the other version of carbonyls, more oxidized. So carboxylic acids and their derivatives. And so what we were just talking about in oxidizing alkenes or alcohols, we were oxidizing to aldehydes and ketones, and we had to be careful not to go all the way to carboxylic acids for those guys on the end. So it stands to reason that we might be curious if we could go the other way. Could we do a reduction and go from a carboxylic acid level redox carbonyl, do some reduction to get to an aldehyde or ketone level carbonyl? And the answer is we do have some ways to do that. One of which you've seen already, which was Friedel-Crafts acylation. Technically, this is a redox reaction because the carbonyl, this is an acyl halide, or it's also called a carboxylic acid chloride. This carbonyl is at the same redox level as the carbonyl of a carboxylic acid. It's derived from a carboxylic acid, and so when we use this molecule in the presence of the aluminum chloride catalyst, the electrons for the reduction of this carbonyl come from the ring, and you make the bond, and so this carbon has actually been reduced from this carbon. And so we could use that to make aromatic ketones. It had some limitations. Remember, you couldn't have amine type nitrogens on the ring, and you couldn't have electron withdrawing groups on the ring. But that, of course, worked in your favor because this wouldn't have multi-substitution either. And so we did accomplish this idea of doing a reduction to get to here. So then that begs the question, this one is specifically for aromatic ketones. Are there any other ketones that we could make with a similar kind of redox management tool? And the answer is going back to lithium dioorganocuprates in chapter 10. So let's review that for a second. So if you had an alkyl halide and you treat it with lithium at the elemental level, you can make lithium, organolithium compounds. And so this carbon, whoever's directly attached to this halogen, had positive character. Now that it's attached to the lithium, it has negative character. And it's going to have a lot of negative character. And so you've done a redox step there. Now, if you look at the periodic table, copper is a lot closer to carbon than lithium is. And so in this next step, we treat the organolithium compound with cuprous iodide. And by introducing the copper in between here, the carbons that are directly attached to the copper still have negative character, but it's not nearly as polar of a bond as what you had when it was directly bonded to the lithium instead. And so what we did in chapter 10 is we took these lithium dioorganocuprates, which are also called Gilman reagents, and we did a coupling reaction. So this negative character carbon and this positive character carbon back in another alkyl halide would couple together, and we lose part of our carbons as waste in this leftover material. And so it turns out that we can use those same lithium dioorganocuprates with acyl halides, and now they don't have to be aromatic. This doesn't have to be aromatic, so we can make any kind of ketones with this, with the exception of we will not be able to make alpha-beta unsaturated ketones. We'll talk more about that later in the chapter. But any kind of alkyl groups on this side and this side will work to make ketones out of these two pieces. And you still have some carbon waste. We can't really get around that. So here's some examples. So this is our classic Friedel-Crafts example. Benzene and an acyl halide, and we make acetophenone, which is an aromatic ketone. If we have an acyl halide with an alkyl chain on it and a lithium dioorganocuprate, we can make a ketone where there's alkyl groups on either side. It doesn't really matter which side is which, but we usually, because remember we were going to waste part of the carbons that came along in this reagent, so we would usually waste the fewest number of carbons. So if we're trying to make this ketone, we're only going to waste one carbon instead of a whole bunch of carbons. Okay, so let's go back again to review something else, which is the reducing agents that we've been using that are in the family of hydrides. And remember, hydride is a hydrogen with a pair of electrons. So anybody whose name is blah blah hydride is going to deliver a hydrogen with a pair of electrons. And I set up a little grid here based on boron and aluminum, which boron is in the quote-unquote first row, and aluminum is right underneath that in the periodic table. And these guys are Lewis acids because there's an empty orbital on the boron and also in the aluminum. So we studied them from that standpoint. And if you fill that empty orbital with a hydride, then you can make, like from sodium hydride, you can make borane into sodium borohydride. And similarly with lithium hydride, you can get from alane to lithium aluminum hydride. And so all these guys actually can deliver a hydride. And the aluminum versions are always stronger than the boron versions in the same situation. And the parent, which I'm going to call these guys, borane and alane, the parents, the parent is stronger than the derivative. And by stronger, I mean better able to deliver a hydride. And also, one thing you may realize is, if you follow these little arrows, is that the borane is about the same strength as lithium aluminum hydride. And so we're going to actually make some other derivatives. And so there's one called diisobutyl aluminum hydride. It has only one hydride to deliver, and it's got these isobutyl groups on it, and so it's a little more crowded. And so it's in the same family as these, but it's been modified so that it's not quite as strong as either of these. And so I'm going to put it on this side, and so actually both of these guys are stronger than this. And here's a picture of it. So the aluminum is connected to the two isobutyl groups, and then there's one hydride to deliver. So we're going to abbreviate it as DIBAH. And this will work on esters. Now, esters are carboxylic acid derivatives, and so that carbonyl is at the same redox level as a carboxylic acid. And this material is strong enough to react with that level of carbonyl, but it doesn't bother the aldehyde. And also, one reason is because there's only one hydride to donate. And so if we put in a 1-to-1 ratio, and it's going to be pretty well behaved, that it will react with these guys and not with these guys. And it works for a lot of different esters. So that is the end of the nomenclature and the preparations that we've seen, a couple of new ones, and we've reviewed older ones.